Okay guys, I hope you're keeping well. This is the fourth version of this video I've tried to make. Version 1 I tried to make in school, my computer crashed out. Version 2 I just tried making a few minutes ago, but I got a bit frustrated by my phone ringing all the time and kind of got a bit sweary, so that was a bit of a poor role model, so I had to cancel that out. And number 3, which I just made a moment ago, I used a phrase that I thought would send everyone into an innuendo kind of cascade. So let's get back to being a bit more professional and robust in our first homework question of the year. All right, guys, so we're going to look at the higher level 2023 question 7. Now, all of the, in every paper in physics, the first theory question is always based on mechanics. Sometimes it could be something tricky like harmonic motion, circular motion, but this one is all about Newton's laws, forces, Suvat stuff, and breaking components into vectors. So let's give it a whirl. Might be useful to watch this before trying this week's homework question, in case it helps you along the way. Now, another kind of word of warning here, guys. I'm making this at home. As I say, I thought I had made it at school until my computer did not cooperate. I don't have the same resources here at the moment as I do at school. Just from summer mode, I've left a lot of stuff in school. So I don't have my logbooks to hand, for example, or I don't have a hard copy of the question. So I'm working off a screen grab of it. So for your own kind of convenience, make sure you've got the question in front of you. Okay, it's from 2023 question 7. I gave you the handouts, but if you've misplaced them, if you go on to the assessment website, past papers 2023 question 7. All right, let's get cracking. I'm only going to write down kind of tricky stuff. Some of this might just be verbal. So let's start off with, just keep the video length minimal. So part I, state Newton's third law of motion. Okay, well, Newton's first law of motion is that an object will stay at rest or move at constant velocity unless an unbalanced force acts on it. The second one is that the force is proportional to a rate of change over time. So the change of momentum, rate of change of momentum over time. And the third one, the one they're looking for here, is the one that for every action there's an equal and opposite reaction. But the more wordy version that it's safe to stick with is that if body A exerts a force on body B will exert a force of equal magnitude but opposite in direction onto body B. So for every action there's an equal and opposite reaction. Okay. Part II. This tripped up a lot of people, this derivation. Now, it's in those notes I gave you that I wanted you to go over before trying the question. But if you skipped past it, or if it evaded your memory, let's have a look. Basically, they want us to go from Newton's second law of motion, which states that a force is proportional even, excuse me, Mr. Bond, to a change in momentum over time, or the rate of change of momentum. Okay, so let's think of what momentum is. Momentum is mass times velocity, okay? So the change in momentum will be your final velocity minus your initial velocity. So what's been the change? So it's mv minus mu over t, and the force is proportional to it. Now, all of this is in your logbook, guys. It's, sorry, that may be blinding things out. Hopefully it's a bit better. That's in your logbooks. All of this stuff, this Suvat stuff, is in and around page 50. Normally at this point, I take out the logbooks and show you, but as I say, I thought I had to say it here. I do not. They're at school at the moment. And remember, when you're doing these practice questions, have your logbooks with you. You have them on the day, so this is what we're trying to simulate and train for, is to have it to hand, because it will save you a lot of time and hassle. If you're more comfortable with it from having practiced, you're going to save a lot of time in the day, and you'll know what's in there and what's not in there. So this is in there. The force is proportional to the rate of change of momentum. Okay, so we need to get from there, and they want us to go from this to the special case of F equals ma. The one you might remember from junior cert, and that's also very washed out. Sorry about that, guys. That hopefully is a bit better. Okay, so to go from here to here. All right, well, let's start off by taking the common factor. I'll just get rid of that. That's our target. That's where we want to end up. So first, on the top, I've got mass times v and mass times u. So let's get that out of there. Force is proportional to mass multiplied by v minus u. All of that's over t. Okay. Because of acceleration being a change in velocity over time, so that's what acceleration is. Acceleration is change in velocity over time. Final velocity minus initial velocity over time. So this chunk here is the same as acceleration. So we can go to F is proportional to mass times acceleration. And we're not a million miles away from our target here. But to go from proportional to equals, we have to realize that we can't just lash in an equal sign. There's some number, which we're going to call k. All right, that's going to be our constant of proportionality. multiplied by ma. Now don't panic. I know you're probably wondering, like, where's this an extra letter from? An extra letter is like the last thing we need. But don't worry, we're going to get rid of it pretty soon. We're going to eliminate it. But this just states the strength of the relationship. So force is proportional to ma just means that if you increase the force, you increase the mass times acceleration. So if this doubles, this doubles. If this halves, this halves. We're just looking for, sorry, beg your pardon, I went a bit of a presumptuous there. It just means that the increase is related. I'm very sorry, I made a huge mistake there a moment ago. It doesn't mean that if this doubles, this doubles. It will eventually, in this special case, but all it means is that as this increases, this increases. As this decreases, this decreases. But we don't know what the factor is here. Okay, how much, what's the strength of that relationship? That's what this K is going to tell us. Okay, now the next step, just after introducing it, we're going to eliminate it. We're going to get rid of it. Because from the definition of what a Newton is, all right, a force of 1 Newton gives a mass of 1 kg, an acceleration of 1 meter per second squared. So from the definition of the Newton, this K is going to be 1, because 1 Newton is going to give 1 kilogram a mass of 1 acceleration. So K is 1. That gives us F equals ma as described. Now look, there's a virtually identical version in the notes I gave you with a slightly more eloquent version of this last step there. We're going to leave all this in for posterity. Okay, and that's what they asked for, F equals ma, prove the special case. So that was part II. Part I was the Newton's third law of motion, and let's keep cracking on. All right, first one is, part 3 is the first time they've asked us to do a bit of maths on this. So let's just write out what we have. A force of 6.8 kilonewtons. So 6.8 kilonewtons. And I'm going to convert that straight away into newtons because I don't want to be tripped up later on. So 6.8 kilonewtons, that means thousands of newtons. So that's the actual value of newtons, 6,800 newtons. Is applied to a golf ball at rest by the head of golf club. The ball has a mass of 45.6 grams. I was just getting ahead of myself there because I'm going to convert that into kilograms. So there's 1,000 grams in every kilo. So we're going to hop that decimal 3 times. So that is 0.0456 kgs. So we have our mass. What else have they given us? They say that it's at rest. So the initial velocity is 0 meters per second. That could be useful later on. It probably will be. And the contact time, the time of duration of the club being in contact with the ball, is 0.51 milliseconds. Okay, now that's not meters. See how tempted I was to write that as meters per second? That's milliseconds. You can tell because in milliseconds, or when the 2 units are written beside each other, that means milliseconds as opposed to meters and seconds. A bit confusing if there's a gap in between. But anyway, this is milliseconds, thousandths of a second. So let's convert that into seconds first, because otherwise it's going to be really annoying. 0.00051 seconds. This is where I made a mistake on, I know, the third or fourth version, whatever version we're on now. I left out a 0 error, and my answer was like 10 times what it should be, like Superman hitting the ball kind of thing. But now we're in the right place. We've got our time, we've got our mass, we've got our force. Okay, so the equation that we're really going to find useful here is, again, from the logbook and from what we just used. The force is a change in momentum over time. Okay, basically what we had earlier on with the K equals 1 thing, just kind of out of the equation to make life a bit easier. So we have the force, the momentum over time. Okay, and what are we looking for again? Oh, we're looking for V, isn't it? Focused like a laser, guys. All right. Calculate the velocity of the ball immediately after impact. So V is our target. That's what we're looking for. I should really have kind of focused on that. So this is what we're looking for. Okay. Well, again, let's just be a bit smart about this. Let's take M out. So F equals M multiplied by V minus U all over T. Because U is 0, this is just going to go away. So we have F equals mv over t. The force is the mass times the final velocity divided by time. And we're looking for final velocity. So it's a little bit of algebra. Bring the t across, or multiply both sides by t. And then bring the m across, or divide both sides by m. And we have ft over m will give us our velocity. And let's just plug the numbers in. So the force is 6,800. multiply the time by 0.00051. I'm going to lash these guys in brackets so we can do it all in one step. Divided by the mass of 0.0456 gives us our answer of, now it'll give it to you in fraction form, 1445 over 19. We want, like, no one can really make sense of that. Well, maybe you can, I can't. Press the SD button, and it will give it to you in a decimal, and that's 76.05. And I just rounded to 05 because we don't need all these other decimals. 2 places is plenty for this case. And remember, this is velocity, so it's meters per second is our unit. Okay, and there's our answer. Okay, so that's part III, Captain. All right. Now, part IV doesn't need this by the looks of it, but that's going to be pertinent later on. Let's just kind of come back to that in a few minutes. Okay, part IV, draw separate diagrams to show the forces acting in the ball, A during impact and B immediately after impact. Okay, so let's do A first, B over here. So this is during impact and immediately after. So we have our ball. Now let's think about beforehand. You've got the weight of the ball pulling it down all the time, it's always there. And then when the golf club hits it, it applies a force. Let's call it force from the club. And that's kind of it. That's all the forces acting during the impact. Weight pulling it down, and the force from the club hitting it in that direction. Immediately afterwards, a little bit more complex. Well, sorry, not complex, I beg your pardon. It's actually a little bit simpler. We have the ball. It still has weight, all right? It's not gone into space unless, again, Superman. So it still has weight pulling it down. This time, this force is gone, all right? Once the club has imparted the ball with motion, it's left behind. The club's over here. So it's not going to be giving it any more force. It's a one and done. It's boom, gone, up she goes. So there's no more force pushing it in this direction. It's immediately going to start slowing down. In fact, you've actually got air resistance and friction starting to work. Now in this question, because they say immediately after, you can expect this to be negligible. There's practically no friction at this point. It will build up, you know, more and more as the ball's moving along and hitting more air particles. Really all they're looking for here is during impact to label the force from the club and the weight, and after the weight. They're not going to punish you for adding in friction here, but they're not really looking for it either. Okay, they will punish you for leaving out any of these three. Okay, so that's A and B, and that's part IV done. All right, and we're on to the kind of really, definitely the trickier end of it for here. So we have part V, calculate the maximum height reached by the ball. Okay, so let's just sketch it out again. There's our ball. It's got an angle of 15 degrees and an initial velocity of 76.05 meters per second. Now basically, this is going to be a SUVAC question. How long does something stay in the air and how long does it travel and stuff? But we need to break this vector down into its vertical and horizontal components. Like how much of this 76.05 is vertical and how much is horizontal. And for that, we're going to need the trig. So we'll call it initial in the y direction, going up. And that's given by multiplying the sine of the angle of 15 degrees multiplied by 76.05. And the horizontal velocity is the cosine of the angle, 15 degrees multiplied by 76.05. So let's do these real quick and then we've got them good to go. A quick caveat on this, guys, is make sure that your calculator has D there. I'll just kind of move this back in so you can see a bit more. I know it's washing out the page, but it'll make this easier. Make sure there's a D on the calculator for degrees and not an or for radians. If it doesn't have a D for degrees, press Shift and Mode. And then we're looking for degrees, which is 3, and now we're good to go. That might vary a little bit based on calculator, but you want to make sure that there's D for degrees up there. Okay, so what are we doing here? We're doing sine 15 multiplied by 76.05, and that's, oh, made a mistake there. I see the way my calculator is trying to do sine of 15 times 76.05, so in brackets, the sine of 15 degrees times this should give us a more sensible answer. 19.68 meters per second. And, excuse me. Let's go for the cosine. Oops, trying to be lazy. Cosine of 15 multiplied by 76.5. will give us 73.46, we'd call it, meters per second. Okay, what is that giving us? It's telling us that of the initial velocity, most of it is horizontal because it's not at that high an angle, and some of it is vertical. So now we've got our, it's going to put a light on here. Hopefully a bit easier to see what's going on. Okay, so we have our horizontal and vertical components of the initial velocity. Now, they're going to be useful in a minute. What's the first thing we want to do? Calculate the maximum height reached by the ball. So we're just dealing with verticality here. How far does it go up before it comes down? So let's SUVAT this. S-U-V-A-T. Now what are we looking for here? We are looking for the maximum height. So that's our target. What is the displacement? How high did it go up? We know that its initial velocity is the vertical component of its overall velocity, which is 19.68. Okay, let's think about its final velocity. Well, that ball, ignore the horizontal. Well, actually, no, let's just do a little trail. There's its path, right? So it's going up, 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 down, 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 down. We're looking for when it is at its maximum height. And when it's at its maximum height, it's essentially going up and then down. But we're looking for what is its velocity here. And in the vertical direction, its velocity is 0. Once at that exact moment, it's not going up, it's not going down, its velocity is 0. It's still going across, but it's not going up or down. So its vertical velocity is 0. And all of this, guys, is in vertical at the moment. Okay, let's talk about gravity. Gravity is pulling that ball down all the time. And it's pulling it down with an acceleration of 9.8 meters per second squared. But we've got to be careful here, because if we've given this a positive value, that means the up direction is positive and the down direction is negative. So acceleration is minus 9.8 meters per second squared. Okay, so we need our equations of standard motion. These are on your logbooks around page 50. We have v equals u plus at, that's definitely 1. We have v squared equals u squared plus 2as. And we have s is equal to ut plus half at squared. Now I'm 90% sure that's correct. If it's wrong, that's going to be an interesting conversation with you. But for now, remember those are in the logbooks. You don't have to memorize them. I just use them a lot, so I know them. Now what we're doing with the SUVAT stuff is we have one thing we're looking for s and 3 things that we do have of information. So we're looking for an equation that has s, u, v, and a in it. Okay? So let's see. This first one is no good to us because we don't know what t is. We could use it to get the time and then work on, but we could do this in one step if we're a bit smarter. S equals ut plus half at squared. Again, we don't know what t is. But look at this guy. V squared, well, we have v. U squared, we have u. A we have, and we're looking for s. This is the winner. This is what we're going to use for this one here. Okay, so v squared equals u squared plus 2as. Now I'd suggest always write it out, okay? So that if you screw things up, the examiner will see that you're on the right track. So here we've written out what we have, identified the formula that we're going to use, and now we're just going to do a little bit of algebra and sub some stuff in. So our target here is s. So let's do a little bit of rearranging. V squared minus u squared, just bringing u squared across, is equal to 2as. And we're looking for s, so let's get rid of this 2a and bring that across. It was multiplied by the s here, so it's going to be divided by over there. V squared minus u squared over 2a is equal to s. Alternatively, you could think of it, what we're doing here is we're subtracting minus u squared from both sides here, so it cancels and moves over here. And here we're dividing both sides by 2a to cancel that, and we're dividing over here. Both the same thing in essence. Okay? I prefer the second, but I know that people prefer the first. So we have a formula. Now it's just a matter of plugging in the numbers and seeing what that height is. So v squared, well, v is 0, so that's 0, minus u squared is 19.68. We've got to be careful here because it's minus this squared, not minus inside the bracket squared. So it's minus 19.68 squared divided by 2 times the minus 9.8 multiplied by here, so be careful. So essentially here, the minuses are going to cancel each other out. Okay, so what we have is 19.68 divided by, sorry, 19.68 squared divided by 2 by 9.8. So that will be, just, I don't want to do this in one step because that looks messy. So minus 19.68 to be squared, and here we have 19.6, and that minus got to cancel that much, just in case you're wondering what happened there. Okay, so we have 19.68 to be squared, divided by, in the brackets you have 2 times 9.8, or you have the 19.6, that's me just cheating a little bit. And we have, well, not cheating, but trying to show you where it came from, 19.76 meters. And there's our answer. So 19.76 meters is how high it went. So that's our displacement, 19.76, and that's in the vertical direction. Now I'm going to cheat a little bit here, because for the next part, they want us to say how long does it take to travel 280? And to make our life a little easier here, if you know how long it's in the air, then it becomes a lot easier to do the second part. So just to complete the picture here, I'm going to find out what is the time, how long was it in the air for? Because some of this doesn't transfer, right? I mean, this 19.68 is the vertical component. The minus 9.8 is the vertical component. Not all of this is going to be the same. And the vertical distance is going to be different from the horizontal, but the time it's in the air is going to be the same. By which I mean, the time that it's in the air for its vertical component is going to be the same as the time it was in the air for the horizontal. It's going to make our life a little easier here. So let's just find out what the t is. So let's use the easiest one. We could use any of these now, right? We have like all 4 except for t. We could use any of these that has a t in it. Let's just keep it simple. Let's use v equals u plus at and just find out what that time is. So v equals u plus at. V is 0, u is 19.68. That's kind of convenient. Right, this is what it is. Plus minus 9.8 times t. Here, look, making another mistake, guys. Sorry, this is me being a bit sluggish. It's late in the day. Let's do the algebra first, okay? So v minus u is equal to at. We're looking for t, so let's bring the a across. V minus u over a gives us our time. V minus u, well, v is 0 and u is 19.68. So that's minus 19.68 divided by minus 9.8 for the acceleration will give us the time. It's going to be around 2 seconds. 19.68 divided by 9.8 gives us our time of 2.008 seconds. So that's how long the ball was in the air, okay? And it'll make sense why I'm doing this when we look at part VI. Now I know this is probably already a very long video, but we're almost there, folks, okay? So let's go up here, VI. And obviously I'm explaining everything, that's why it's going to take a long time. You don't have to explain all of it when you're doing the question. Okay, calculate the time it takes for the ball to travel a horizontal distance of 280 meters. All right, let's see about this. This time we have horizontal distance is 280 meters per second. We have our horizontal component from earlier is 73.46 meters per second. And we have our time, which you might not even need, is 2.008. Oh, lads, okay, I really have screwed up. Now, I've screwed up in a good way. This should be our final answer. Okay, it should be in the air for foolish man, being me, not you. Okay, ignore this. That was the time it took to reach the apex before coming down. So its overall time is going to be 4.016 seconds. Bear that in mind, folks, okay? Because now I was going to make our life so much more complicated. Let's take a step back. We have a distance and we have a velocity. We don't care about acceleration. Here we can ignore things like wind resistance and friction and stuff. So all we have here is, I'm going to just change the rhetoric a little bit here and say speed is distance over time. Or no, let's not. Let's keep it good. Velocity is displacement over time. And we have velocity, we have displacement, we're just looking for time. So bring the time across. Time times velocity is equal to displacement. We're looking for time. Time is equal to displacement over velocity. So we have a displacement of 280 meters divided by a velocity of 73.46 meters per second. So 280 divided by 73.46 gives us 3.811 seconds. Okay, a little bit off from the 4.016, that's rounding errors. So 3.81 seconds is how long it took to traverse that distance of 280 meters. Okay, that's the second and last part. You can tell I'm flagging a little bit here myself, guys, but let's power through. This is the last section. Okay, a wind blows as the ball travels through the air. The wind has a velocity of 8.2 meters per second east. Okay, so north, south, west, east. So it's moving, the wind, I beg your pardon, has a velocity of 8.2 meters per second east at 3.7 meters per second north. Okay, this is again all about breaking vectors down into their components. And here, we're given the components and we're looking for the resultant. So imagine that something's being pushed this way by this amount and this way by this amount. What is the overall displacement? And really what you're looking for here, it's just a triangle. It's this bit of a right angle triangle. So we've got 8.2 is that, 3.7 is that, and we're looking for the displacement, like the, sorry, beg your pardon, the magnitude of it and the direction. So let's get the magnitude first. And that's going to be Pythagoras all day long. A to be squared plus b to be squared equals c to be squared. So if I take 8.2 squared plus 3.7 squared, it will give me whatever c is squared. So let's do that real quick. 8.2 squared plus 3.7 squared is equal to whatever that is. And let's get the square root of the answer. And we have 8.99. 996, about 3 decimals, really 9 essentially. So it's 8.996 meters per second, because remember this is the wind we're talking about, so it's going in that direction by 8.99. Okay, now as for the direction, we're going to need to use a little bit of trig here. So we have this angle, is what we're looking for. Now in terms of that angle, which we're going to call theta, we have the opposite and we have the adjacent. Okay, and we're looking for what is this. So if you think about the trig ratios, we've got Celia Old Harry chased a horse. This is how I do it. Through our attic. If you prefer Sakatoa, no hassle, whatever works for you. But we're looking for something that has opposite and adjacent in it. Tan is your man. So the tan of the angle that we're looking for is equal to opposite over adjacent, 3.7 over 8.2. So if we get the tan minus 1, the tan inverse, 3.7 over 8.2 will give us that angle in degrees. So we got 3.7 divided by 8.2 will give us some random number, 37 over 82. And I want the inverse tan, so shift tan answer. It gives me 24.285 degrees. That's plenty of precision for them. Okay, so it's got a magnitude of 8.996 and a direction 24.285, and that's, you've got to be careful here, that's northeast, okay, from the horizontal. Right, I'm going to stop this video before it becomes even more of a monster, but hopefully you're still with me to some extent. The chapter to really look at here is the forces one, and also the one about breaking vectors into their components. And I'm going to stop talking now because I've been talking quite a while. Alright, talk to you in a bit, bye.